So hi, we're at half strength today, and so I'm going to record today's lecture so that all of you who are following along at home can track. And we hope you are well wherever you are. Our plan for today is to talk about algebraic addition and subtraction and scalar multiplication. And what I aim to do is to introduce notation using the unit vectors I and j, that and k if we need it for three-dimensional notion, that will help make some sense of what we're doing here. I want to try to get across two things at once, and the first is that if we can do analysis, if we can analyze, how about if we can spell? If we can analyze using vectors as objects, we don't have to and in particular, find the midpoint of the segment connecting points A. This is a typical kind of a problem that we can solve with vectors as objects, never having to refer to any sorts of components, polar form, or anything like that. Take your points A and B, like so, and create vectors from the origin. So this vector A will represent our point A, and this vector B will represent our point B. And now the midpoint here of the line segment connecting these two is going to be the point that is halfway from A to B. But the vector connecting A and B is literally B minus A. Look, tail to tail, connect. So this vector is B minus A. This vector should get me to my midpoint. So this vector right here should be a half of B minus A. And look, the red vector A and the vector 1/2 of B minus A are arranged head to tail, and therefore the vector that connects straight across is equal to A plus a half of B minus A. That's our solution, M, midpoint that we're looking for. And when I add these, when I simplify these using our vector addition rules, I get A, a half of B, plus A minus a half of A, plus a half. And so I discover that the midpoint of the points A and B is kind of what we suspected. It's the average of A and B. And I discovered that using vector analysis without any reference to components. This is the power and the beauty of vector analysis. And anytime you can do this, we will. There's a very good, I don't remember if I assigned it, there's a very good pirate treasure problem that uses this idea. And it's in your book. I'll go through to check to see if I did we'll give it to you because it's a written problem. So this is the spirit of analysis without components. But having done this, there are going to be times when we actually need to use components. And for our work, those times are going to be frequent. And so let's talk about how to do that. What we're going to do is to put our vectors into a coordinate system. And when we put our vectors into a coordinate system, we have a choice of placing them into a polar coordinate system or placing them into a rectangular coordinate system. And if we place them into a rectangular coordinate system, our vectors, so here's A. And now I can think of A, it is convenient to think of A in terms of its projections onto the x and y axes. Here and here. You can think of these as shadows falling onto the axes. And when we do, we get a certain length, ax, that we can actually think of as a vector in this direction. And we get another length, ay, we can actually think of as a vector in this direction. And I'm going to move that vector over to here. F. And you can see that when I add the ax component and the ay component, head and tail, like so, what I get is the whole thing, A. Just like that. Let's spin this out a little bit more. When I look at the ax, it occurs to me that I can think of it in terms of scale like this. Let's take a vector that is going to point in the direction of the x-axis and have a length of 1. We call such a vector a unit vector. So a vector in the direction of plus x and a length of 1, which is a unit vector. And we're going to think of the x component. We're going to call this vector I with a hat. Likewise, we're going to have a vector in the direction plus y and a length of 1. We're going to call that vector J. And if we needed a z component, then we would have a vector in the direction plus z and a length of 1. And we would call that K. Yes?
Positive x and positive y plus z are like along the axis.
Exactly. Yep. So I is this guy right here, and J is going to be that guy right there. And now we can think of ax as a stretch of I. In other words, a scalar multiple. So that what we have here, really, as a vector, is ax. The vector is equal to the length ax. Ax, the vector, is equal to the vector I stretched by a factor of ax, or its component. And likewise, ay, the vector, is equal to ay times the unit vector j. So that when we put it all together, we have a fairly elegant representation, and that is this, that the vector A that we have is equal to ax times I plus ay times j. And we call this the rectangular representation of A. here's the set of vectors I and j, and k if we need it. The basis of the vector space. In this case, our vector space is R2. And by basis, I mean something specific. I mean that every vector in R2 can be represented as a combination of i's and j's. And a unique combination of that. Now last year we did the same thing, but we had a little bit of interpretation for it. We represented our vectors last year with these angle brackets. And we put the components inside there. And there's actually nothing wrong with this either. In fact, mathematicians will use this notation a whole lot, so will physicists. The reason that I prefer this a little bit is that it makes this more explicit that what we're really doing with these components is adding up vectors in order to get the whole thing. And that's going to become important later when we change or rotate our reference frames and we have different basis vectors. Now, the real purpose behind writing a vector in its rectangular representation is to make addition and subtraction easier operations. Yesterday, when we added vectors, what we had to do was to do a geometric addition of vectors by taking A and taking B and placing them head and tail and connecting them. And the best that we could hope for was about 2 significant digits of precision, because it was imprecise, because the protractor and the ruler are really inadequate measuring tools for getting 3, 4 digits of precision. So there's limitations on what I can do with the geometric addition because it's imprecise. Also, we noted that if I want to get measured results as opposed to quick and dirty, I have to take some time to do it, right? I have to sit there with the protractor and ruler and draw one vector, draw the other vector, etc. So geometric addition gives us great pictures, and it's useful for quick and dirty, just to get a sketch, to get an idea of what it's like, but it's not very good for numerical work. So if I all I want are results that are good to about 10 or 20%, I'll do geometric addition, just sketch, go. But if I want something that's good to, say, 1%, then I would have to actually pull out the ruler and protractor. And if I want something that's good to 0.1 or 0.01%, I just can't with geometric. So instead, the algebraic addition, which we're about to do here, can give me as much precision as I want. It takes slightly more time and notation than a quick and dirty geometric, but it is much faster than the time-consuming precise geometric, and it has essentially infinite precision. So this is going to be the tool of choice for us. And here's how it works. It's really beautiful. Let's say I have A, and And let's say I have B, like so, and I wish to add them. And so I visualize A as the combination of AXI plus AYJ. And I don't put the vector hats where the context doesn't really, it makes it clear. And I also am going to write BXI and BYJ. Notice that BY is going to be a negative number in the standard reference frame here because B is going down. And now this is really simple. Watch what happens. Because of the associativity and commutativity of addition, I can now group all of my i's together and all of my j's together, and I can add them separately without interference from each other. So that what we get is simply the sum of the x's in the I direction, and the sum of y's in the j direction. We're done. So that adding vectors is really adding component-wise the i's and the j's, and if necessary, the k's separately. We call this the linear independence of our dimensions I, j, and k, or unit vectors I, j, and k. And it leads us to a slogan that you may remember from last year: what happens in the x stays in the x. So this is all nice and theoretical, but how does this work out in reality? As soon as you guys are ready to go, I will show a couple of examples. As an example, suppose Marcia drives from the origin to 4.3. She then drives, to make this miles, she then drives 5 miles east, 2 miles south, and 6 miles west. What is her displacement? You can practically solve this problem in your head faster than I can write it. We can think of her motion as taking place in 4 different pieces. And we can represent that first piece as the displacement from 0, 0 to 4,3. And that displacement is going to be 4i plus 3j. And then her second displacement is going to be 5 miles east, which we're going to represent as 5i and 0j. And her third displacement we can represent as 2 miles south.
0i minus 2j.
You got it. And her fourth displacement is 6 miles west,
Negative 6i plus 6j.
and now we add them up and move them out, and we get
3i plus 6j.
and that is your overall displacement. See how elegant that is? And it's so elegant that probably you could do that in your head just by keeping track of the x's. 0 to 4 plus 5 minus 6 is 3. 0 to 3 minus 2 plus nothing is 1. And we have 3i and j. So this addition of vectors in rectangular form is a really powerful tool because it can be done in your head. Now, if my vectors are represented in polar form, things are a little uglier. Ready? Oh, I see something purple.
What would be I and J for the answer?
The I and the J in the answer are the unit vectors that point in the x and the y directions, respectively. So that we're assuming a reference frame here, and in fact, our reference frame for this problem was sort of implied north, south, east, west, like so. And so I is right here, and J is right here, and that gives us a nice coordinate system with I and j as the basis vectors. And the displacement of 3i plus j would then be I times 3, or 3i, plus j is my overall displacement.
Okay, well, there was E1.
Ah, so their magnitudes are always 1, but their directions are different.
Okay.
In fact, we can think of any unit vector, whether it is ij or in some random direction. We can think of a unit vector as really just a direction. Okay, so let's consider now what happens when we have vectors given to us in polar form, which happens often. Marcia drives from the origin to a point 5 miles at an angle of 37 degrees. She then drives 3 miles northwest and 2 miles west. What is her displacement? One second. Okay, so what is her displacement? Now, we need to visualize this just so you can see what we're talking about here. So we start at the origin, we go up 5 miles at an angle of 37 degrees, like that, and then we go 3 miles northwest, and then we go 2 miles west. So we're, somewhere over here. It's a little bit unclear whether we're going to be on this side or that side of the y-axis. All right. If I'm going to add these vectors, like so, it's fairly evident that I'm going to need to represent them in a rectangular form to do so. Because I can combine x's and y's separately, but there is no independence of vectors that are at random directions. I won't prove this, but the independence of the x and y, the I and j, really come about because they're perpendicular to them. And so, because vectors in polar form are not generally independent of one I first have to represent them in rectangular form. So here we go. Let's farm this out. 5 miles at 37 degrees, rectangular form, go. 3 miles northwest, rectangular form, go. And slowly walks out 2 miles west, rectangular form, go.
Forward.
Negative 2.1, 2.
And just to get in the spirit of it, I'm going to encourage you to say it with the I's and J's. Very good. And now, having done this, we can add up, and we get negative 0.1i plus 5.1, which we see now why we were so ambiguous about which side of the axis this will be on. This is just barely to the left of the y-axis. Notice that a quick graphical, as I did right here, helps keep our head straight, especially with sign problems. If I get a result here that doesn't look like the result that I get here, then that tells me there's an inconsistency that I need to hunt down. Now, a question of style. This is a perfectly good displacement right here, and under most normal circumstances, I'm going to accept such a displacement. However, in terms of style, if your original vectors were given to you in polar form, generally speaking, the person asking you the question will expect an answer back in polar form. So, I've got this delta x right here, but I should probably convert it into polar form in order to complete the answer. So, go ahead and do that. What do you got? What do you notice about the magnitude of this vector? Yep, that's exactly right. Here is a bit of folklore about vectors that everybody should know. And that is that if you have a vector that has a really large component in one direction and a really small component in the other direction, then the magnitude of your vector is going to be essentially equal to the magnitude of the large component. And you can see here that even though I had a 0.1, then this was still the same magnitude as that, and probably out to about 1,000 clicks. Probably 5.1 or something, right? Yeah. Yep. And that happens because the magnitude of my vector, the magnitude of A, is equal to square root AX squared plus AY squared. And when I square a really small number and add it to AX squared, I essentially get AX squared. And then the square root of AX squared is just AX. Does that make sense? So that's a helpful thing to know. Please notice the notation that we use for the magnitude of vectors, which is the same as the absolute value signs. We're thinking of this as a length for a vector norm. The physicists call it magnitude. The mathematicians call it a vector norm. I want to take a look now at two problems that are given. Maybe one problem is given. And it's number 56 in the book on page 76. And I'm going to take a minute to upload this problem. You guys can take a look at it and see if you can come up with an elegant solution. I'll pause the video while you're coming up with an elegant solution. For those of you following along at home, we are looking at problem number 56 on page 76. And you can pause the video and see if you can come up with a good solution for yourself. Okay, Josh, you've got a solution for us.
Okay, so I looked at the graph and basically I said that it looks like the width of the rectangle in the x direction looks like bx minus ax.
Good. So the width of the rectangle is bx minus ax, and that computed out to be?
That computed to be 4.0i.
Can you give me the computation
Right.
goes?
B of x equals 10.4i.
How computed?
Oh, sorry. 12 times the cosine of 30 degrees
And then minus.
minus 10 times the cosine of 50 degrees.
Good.
Then for the length, it's AY minus BY. So that is 10 sine 50 degrees minus B sine 30 degrees. Or 12 sine 50 degrees.
And that turned out to be how much?
1.66J.
Awesome.
Then to find the perimeter of the rectangle, it's 2x plus 2y. So 2 times 4.0 plus 2 times 1.66 came out to be 1.3 meters.
No way. Not 1.3.
11.3.
Yeah.
Sorry. Brain fart.
Okay. Just very briefly, you may have written this on your paper, but I'm going to encourage consistent labeling. So if this is our width and length, then we're going to use our width and length. Yep. Good. Anybody have some ideas about how to find the magnitude and direction of the vector from the origin to the upper right corner? Can you visualize it in terms of vector operations?
Well, we need
It would be,
the
it would be BX and A1.
Go ahead.
You beat me to the punch. It's all you, man.
Ron.
Well, BX is 10.4 and AY is 7.7. So 2.4, 7.7. 10.4 I plus 7.7J.
So what you're saying is this guy's 2.4. So if I can visualize adding those two together, either this component plus that component. Yes, that works. 4, 5, 6. Excellent. Great. Nice. It was even better than my solution. My solution was visualizing our length that we had computed and adding that to b. And yours did require an addition. Nice. Okay. We have like 3 minutes. I want to talk about number 57 on that same page briefly, because we have not done a whole lot with vectors in 3 space, and you'll have plenty of time for that when you do Calc 3 and linear algebra. But I want to give just a basic operation here. The first is that for vectors in 3 space, the magnitude of R is going to be found by the Pythagorean theorem extended, like so. And the reason for this is fairly simple, and that is that if I have a vector in 3 space, so it's going to be a certain amount, put it on a coordinate, set of coordinate axes here. And so my vector now reaches out over a point in the xy plane, in the xz plane. No, wrong. Mangling my reference frames here. So try again. Here's z, here's y, and here comes x out of the board. So my vector r is going to be over a point in the zy plane, like so. And so if I drop a perpendicular to use the Pythagorean theorem, then this component is just rx. This component right here is the length of the vector in the zy plane, which is going to be the square root of rz squared plus ry squared. So we can say that r squared is equal to rx squared plus the length of this projection right here. Let's call that vector A, which is ry squared plus rz squared. Does that make sense to everybody? Kind of. When I consider the angles between r and each of its axes, then I find something really interesting. Let's take just the z-axis. So here's my vertical axis, and here comes r out of the z-axis. When I consider the angle, let's call this theta z, like so, then I can see that this forms a nice right triangle. There it is. And the component that I can measure easily is the RZ component. So that when I do adjacent over hypotenuse for RZ over R, what I get is the cosine of the angle theta z that the vector R makes with the z-axis. And likewise, Ry over R is going to be the cosine of theta y, and Rx over R will be cosine. We call these 3 numbers the direction cosines for each of the angles, and it's sort of the best we can do in 3 space, because you don't have a single angle. You really have 2 angles, like latitude and longitude, in 3 space.